I'm going to be, as you can see, this is a team effort, very much so, and it's just to recognize the people who have been funding us over the last few years. On the left-hand side, we're part of an organization called the MINEX CRC. It's the Mineral Exploration Cooperative Research Center, which is a collaboration between industry and geoscience, geological surveys and research organizations, with in particular partners in Perth and in Adelaide in South Australia. And we're also part of a consortium that's supported by geological surveys around the world called the Loop Consortium. And the work I'm going to be presenting to you today is a combination of research we've been doing for a few years now, plus some newer work that I'm going to be presenting to you. And the overall aim of it is to develop better ways of modeling 3D geology. And 3D geology means lots of things to lots of people. It can be looking for oil and gas in basins based on seismic. It can be mine scale, so using a lot of drill hole data. But what I'm going to be focusing on today is using regional geological data sets as constraints on building quite large scale 3D models. So we're talking about modeling entire map sheets rather than modeling small deposits or the single sedimentary basins. So just to give you a bit of an idea about the background to what we're doing, people have been making 3D models for a long time. It's not a new idea, and I can show you a beautiful diagram from a patent from 1884, where they were talking about building physical 3D models of mines in order to represent the spatial relationships between the deposit itself and all of the engineering that needs to go into it, the tunnels, the stopes. And so this idea of building 3D models dates long before computers. But at the same time, it's something that was obviously taken off with computers. And if we look at a sort of a time history of 3D modeling, they've got the names of all sorts of different 3D modeling packages listed here. Some of them still exist, some of them no longer exist. But we can break them up into the sort of earlier types of modeling, which was a purely CAD-based modeling where there was a lot of human intervention and not very much geology. We took the geology data and then we tried to manually join up the observations. That was superseded largely in more recent times by implicit modeling systems that try and perform some sort of automated interpolation. And then there's another side to the calculations, which is whether we just are trying to model a static vision of the 3D geology as we see it today, or whether we're trying to include calculations that allow us to remove the displacement on faults or to unfold things. So these kinematic packages, and there's a whole series of these different packages, and they tend to be specialized towards one particular scenario. So they're specialized towards basin studies, or they're specialized towards mine scale studies. And when you look at them, there really aren't any systems that have been developed specifically for the regional scale geology that interests us. And the reason that we're interested in regional geology, well, there are lots of reasons. It can be for an environmental study to look at groundwater issues. It could be for mineral resource exploration, or it can be for a purely scientific desire to understand the 3D geology of a particular region as a way of better understanding the tectonic evolution of that region. So for the last 3 or 4 years, we've been working within the framework of a consortium led by Laurent Taillère at Monash University, called the Loop Consortium. And the Loop Consortium, as you can see, has a whole series of partners. And as I mentioned before, the MINEX CRC is an active participant. And we've divided up the workflow of 3D modeling into three main areas: into the geological knowledge manager. So before we build a 3D geological model, we need to understand more about the geology. We want to get the most information we can out of our existing data sets. So that's one pillar. The second pillar is the improved technologies for geological and geophysical modeling. And the third pillar is the analysis of the 3D models in terms of uncertainty mapping, risk mitigation, value of information, and those sorts of questions. So we're going from the raw data, extracting the most information we can out of the raw data, through to geological and geophysical modeling, and then finally through to what these models are telling us about the questions at hand. And of course, there are many different questions that we can think about. In terms of the work I'm going to present today, I'm mostly going to be talking about the first two areas, about speeding up the workflow and building reproducible models, but I'm going to also introduce some of these other ideas. And if we have time at the end, I'm also going to talk about a second sort of side project that takes a very different look at this whole question of 3D modeling and using geophysics. So we'll see how the time goes. I'm not quite sure how long you want me to talk, but I can talk until you tell me to stop. So when we think about the ingredients of a 3D geological model, we have the raw observations, we have, which might be field observations, or they might be coming from drill core. We have interpretations, so we might have seismic data, but then we need to interpret the seismic data in terms of stratigraphic horizons and in terms of faults. We might have some sort of background concepts as to what we think the tectonics is of a region. So we might think of the system being fundamentally a listric fault with high angle normal faults in a conjugate system. And then in order to turn these into a 3D computer model, we need some sort of algorithm like this radial basis function that allows us to convert our observations and interpretations into a 3D model. And of course, the current systems end up looking something like this, where you have all of your individual sources of constraint, but within the 3D modeling package, they all tend to get muddled up. So you start out adding some data, and then you add some interpretation, and then you add some concepts, and the algorithms are in there somewhere, but it's actually quite hard to unravel what you've done. So one of the aims of the work that we've been doing, particularly at UWA in Australia, is this idea of trying to untangle the different sources of information that go into a 3D model so that we can better understand what the limits of the modeling are. So just before we go further, just to go on a bit about this idea of prior concepts, often, especially at the regional scale, we don't have very good constraints about our 3D models. And so in particular, we don't have very good constraints about the faults and what they're doing at depth, because in the hard rock cratonic areas, often the geophysics isn't very revealing about the downward extent or orientation of these faults. So we tend to bring in our conceptual constraints. So we might think that, as in the top, that it's a fold and thrust system, or we might think that it's at the bottom in the middle, it's some sort of transcurrent system, or the listic system that I showed you before on the right, or some sort of extensional or inverted extensional system. And we use this to fill in the gaps in our data in order to build coherent 3D models. But they really are just conceptual priors. They're not actually data in their own right. And so this is just emphasizing this, that we can see when we look at seismic sections that people have essentially taken these conceptual models, because we know there's very little data at the surface and the interpretation of the seismic, is somewhat ambiguous. And we can see that they've applied on the right-hand side a listric fault model, and on the left-hand side something that looks like a flower structure from a transcurrent fault. And these have been used to build on top of the rather sparse data to produce more complete interpretations. So we see these two types of faults as interpreted in the sections, but we know from the work of Claire Bond that seismic sections, as much as they are valuable, they are open to interpretation, and they're open to the bias of the interpreter. So let's look at two n-member scenarios for modeling 3D geology. So here we have a 1 degree by 1 degree map sheet from the northern part of Western Australia. It's actually from the Hamersley Range. And these are Proterozoic Archean banded iron formations, which have been quite complexly folded with some later or synchronous faulting. And if this is we can see the structural observations that are available, we can see the faults, we can see the geology. And that's an area where we might go, okay, well, this is an area where we think we can build a 3D model based on essentially the surface observations. And when you get to this regional scale, of course, there is drill hole data, but the drill hole data isn't very deep. It might be 100 meters or 150 meters. And here we're talking about 100 kilometers. So the drill holes essentially act as additional outcrop information, not really as giving us real depth constraints on our model. So that's one end member. And then the other end member is something where a geology map looks like this, where all of the surface is covered, maybe by sand or by a shallow sedimentary basin. And then, of course, the map is not telling us anything very useful about what's going on beneath the surface. So in that case, we would probably want to take a geophysics first approach, doing an interpretation of the magnetics or the gravity, the electromagnetic, seismic, whatever's available, MT, in order to try and work out what's going on in 3D, because we certainly can't use the map to do that. And what we're going to talk about first of all is those cases where we've got geology. So we have the Loop information manager, which is a Python module called map to loop that integrates with the other codes. And what we're doing is we can see in the top right, we have a geology map of Western Australia, and we're looking at the little box is the 1 degree square that we're looking at below. And these layers, all this data is stored on a web server, a GeoServer instance, so that we can access the data for the whole of Western Australia online without actually having to open up any files. We can define the rectangle that we want and just download that rectangle of information and then start to work on it. And that rectangle of information contains the geology polygons, the fault polylines, the structural points, and the digital terrain model, which we can all get online from various different sources. So all of this data is available for the whole of Western Australia, and we've got similar systems that we're working on for the rest of the continent. And the idea is to make it, and the dream in the long term is to make it so that we can draw a rectangle around a bit of geology and build a 3D model semi-automatically. So let's see where we've got to right now. The data flow that we have is that we have essentially 4 types of information, plus the conceptual constraints that we might want to apply as to what we think the fault systems are. And the first and most obvious constraint of position, if we know where the contact between 2 formations is from the geology map, we can include that as a constraint. The digital terrain model is obviously a constraint because it gives us the Z component of any particular position. We have gradient information, so we know what the orientation is, the dip of a bed or of any sort of foliation or lineation. We have topological constraints, which are the spatial and temporal relationships, and I'll talk more about topology in a minute. So we have these different types of constraints that are actually provided by the geology map. So the work of map to loop is to take these individual constraints and combine them in such a way that they provide the inputs that 3D modeling packages require. So we start off with these observations and concepts, and we output a reformulated series of augmented data that are in the form that the 3D modeling packages require. So some of the things are fairly simple. For structural observations, we can take in the structural observations from that structure layer. We can combine it with the geological map so that we know which formation the observation belongs to at the scale of the map. And we can combine it with the digital terrain model in order to get the Z component of the observation. In this particular area, it's pretty flat, so the Z didn't matter too much. But you can imagine if you're working in hillier or even mountainous regions, Z becomes a very important part of the story. We also have the contact information, and we've gone from polygons now to lines. And the way we've done that is by analyzing the map and any other databases we have to try and work out what the local stratigraphy of the system is. Because in all of these modeling systems, we either have to define the base of each unit or the top of the unit, and that's what we're doing here. Is we've analyzed the map and we've analyzed the stratigraphic columns in order to work out what the local base of each unit is, and that's we've extracted. And then finally the faults, we're doing similar sort of information of extracting it, and if we have sections, we can apply that too, although I try to avoid using section data unless there's a geophysical constraint for it. So let's talk about topology a bit. Topology is an important aspect of the analysis of geological maps because it provides a harmonized and synthesized look at it. So there's going to be a slight detour now before we get to 3D, just pulling apart the maximum information we can get out of a map. So here we have a part of this same area. It's a slightly smaller area, but we can see that there's a couple of synclines. The Tui Creek group is in the middle of a syncline, and there's a dome and there's some faulting. And what we can do is we can analyze this map automatically to extract all of the different features in the map. So in this diagram on the right, which is a network graph, we have squares, and each square represents one formation in the system. We have triangles, which is the group that that formation belongs to. We have faults, which are circles, and we have lines or arrows which join these different features. So if a formation has got an arrow to another formation, it means that there's a stratigraphic relationship between them. If the fault has an arrow between the fault and a stratigraphic group, it means that fault is cutting the group. If a fault has an arrow to another fault, it means that that fault is truncating the fault which the arrow points to. So we're reducing the complexity of the geological map into something which is into a much easier to understand form, easier to understand for a computer. The geologists prefer the map on the left, the computers prefer the network graph on the right. And the network graph on the right, you can actually build on it even more because you can include information about where mineral deposits occur. So if we look at an example here we're just looking at the distance of each fault to mineral deposits, so that the faults which have the most mineral deposits close to them are highlighted in red, and the faults which are distant from mineral deposits, which are those black dots, and in this case they're iron ore deposits, are grayer. And so we can see, and this is a fairly traditional thing that you've always been able to do, except that we can also do this for individual formations. So looking at which formations have the most ore deposits in them. And we can also do that on if we break up each formation into the local area defined by fault domains. So instead of considering each formation as a continuous area, if it's cut by a fault, we can say, well, this is locally possibly got a different metallogenic setting than the area to the other side of the fault. So it's a way of breaking up the geological map into subdomains that allow us to perform more types of analysis. And the type of analysis we're going to look at, one type of analysis we can do is we can draw these network diagrams and put the minerals deposits within this network diagram. So on the right-hand side, where we have these numbers, the 21, the 14, the 10 in green, it means that that's where the iron ore deposits were. They were mostly found at the contacts between the Brockman Iron Formation and the Mount McRae Shale, or between the Mount McRae Shale and the Wittenoom Formation, whereas some of the deposits are mostly found, are more found within particular formations. And of course, there's a buffer, a length distance that you can put in. And we're going to talk about length in a minute again, and you can vary that length. So we can look at the information of the relationship between structures and formations and ore deposits in map view, but we can also look at it in this condensed network diagram, which is really giving us another way of looking at mineral systems. So it's a condensed way of looking at all the relationships. In this case, it's just the stratigraphic relationships, but we can also do it including faults and other types of structures. We could do it with fold axes, for example. So bringing it all together and condensing it down into something that we can then analyze. But when we do analyze relationships between faults and mineral deposits or stratigraphy in mineral deposits, there's a limitation to the way that it's done at the moment. In the moment when we do mineral prospectivity mapping, we essentially do it in terms of the distance from a mineral deposit to a particular feature. So that would look like the diagram on the left. So if we said, what's the distance from the Turi Creek Formation, which was the middle of that syncline, if you remember, there's basically a linear or Euclidean distance that makes this color map on the left. So the whiter it is, the closer you are, the darker red it is, the further away you are. But there's other ways of doing this, and we can do this by using, for example, the shortest path. And what we're doing in this diagram, and this makes use of those graphs that I was showing you before, is that instead of saying the shortest path is just the closest distance, we're actually using the geological elements in the map to define path length. So we can say, for example, that faults would be faster path lengths than stratigraphic units, with the idea that the faults might be preferred fluid pathways. And we can say that the contacts between units might be faster or slower than the units themselves, and we could define individual units as having higher permeability or lower permeability. Once we assign all of these, we can then work out what the shortest path is by taking into account the faults. And in this diagram here, labeled E, we can see that there are certain lithologies which are closer to this syncline in the northwest of the area, because there are faults that are connecting them to this geological feature. So we can have a more geological definition of distance. We can also do that and then say, well, imagine that these four dark faults were actually active only after the mineral system was put in place. So these are young faults, in which case we don't want to consider them in our distance calculation. And we can see that that changes the apparent distance between features because we've removed them from the calculation. So instead of having a very simple linear distance, we've now got a distance that depends on geology. And as geologists, that in theory at least should be a good thing, and that's still something to be tested. All of this is very much in its infancy. We can also look at another way of looking at it, and you can actually very simply do flow calculations or resistivity calculations. The maths is about the same, where you can say, let's not just take the shortest path, but let's take the most accessible path. And in this case, on the right-hand side, we can see that this Hardy Formation, which is highlighted, is apparently very close because there are many faults that connect it to the Churi Creek Formation in the top left. So there's this idea that having two faults that connect something provides double the permeability than having one fault. And if you have three faults or four faults, then of course the permeability, the apparent distance gets shorter and shorter as all of these geological features become active. So there's kind of an aside to the topic of 3D, except that it's to point out that in our opinion, there's a lot more work that there's a lot more information and insight that we can get out of our maps before we even go into the third dimension that helps us to decide which features we actually want to model in 3D. So let's go back to the 3D world now, and another type of information that in the right conditions we can extract is the apparent fault throw. So we can actually, from our map, we can extract information on the displacements that we can see in our map. And these all calculations are done automatically. It doesn't always work, and so you need to filter out the data a bit, but it gives you an ability to look at variations in displacement, which you can then correlate with damage zones and faults and the amount of permeability that they might have had available to them. You can also do calculations of local formation thickness. So instead of just taking a stratigraphic thickness for a system, you can say locally this formation is thinner or thicker than it is in other parts of the model. And you can even normalize that and contour that to give you apparent changes in formation thickness, regardless of which stratigraphic unit you're in. So all of these automatic techniques are available to us. They can all be improved. They're all proof of concept at this stage, I think it's fair to say. But what we've done is we've provided all of the information that's necessary to build a 3D model. And therefore, there are two packages that we've supported at the moment. One of them is GenPy, which is a package developed by the University of RWTH Aachen by Miguel de la Vaga. And on the right-hand side, within the Loop package, there's a package called Loop Structural, which was developed by Lachlan Gross at Monash University. And they use different interpolation schemes. They've resulted, as a result, the models look slightly different. But the reality is that you're able to extract the information from the map automatically that feeds into the 3D modeling package. Now, first thing to emphasize is it doesn't work for all geology. There's all sorts of complex geology that it doesn't work for greenstone belts, for complex things. But that's the challenge for the future is to extend our ability to analyze maps automatically such that this sort of model building does become an automatic process, because that allows us all sorts of opportunities in the future. So the other thing to emphasize about these two packages, GenPy and Loop Structural, and one of the reasons that we support them is because they're both open source packages, and the codes that we've been developing are open source, which means that anybody can pick up on this work. They can use it as is, or they can include it into their own modeling systems if that's what they prefer. So we can take the observations and we can combine them with the algorithms to build 3D models, and that's something which we can do right now for the geology we have. How we include interpretations, well, we can include them if it's an interpretation, an explicit interpretation of seismic, but one person's interpretation may not be enough, and there may be room for doing elicitation, which means calling on a group of experts to each make an interpretation and to then be able to test the different interpretations. And the conceptual parameterization is still something that we're scratching our head about. So let's imagine that we've built a model automatically, and we certainly can do for the area that we've shown you. That gives us then the opportunity to understand the uncertainty in the model. There's a number of researchers, you can see some of them down there at the bottom, who've worked on this idea of understanding uncertainty in 3D geological models. And so the first idea is, and they essentially all work with the same logic, is that rather than just having a single model that produces a single set of data that produces a single model, we're going to perturb the input data. So we're going to perturb the observations in such a way that honors our understanding of the uncertainty in the observations. So for example, if you measure a dip of a structure in the field, of course, you measure it at 75, but it may be that if you'd measured it 10 meters down the road, it would have been 80, or if you'd have measured it 10 meters beneath the surface, it would have been 60. So there's an inherent one point observation is not all that reliable. So we allow the position and orientation of features to vary, which allows us to predict variations in the 3D geology, which we can then combine to analyze new ways of looking at the reliability of our models in 3D. So rather than producing one model, we produce 100 models, and then we can look at the variations. And in this case, we're looking at the uncertainty box set. So for each voxel in the model, we're saying, how often was this geology the same in our 100 different predicted 3D models? And how often was it different? So if it's red, it was more often different. If it's blue, it was more often the same. So then we have the ability to say, well, in this area where it's very uncertain, maybe we need to collect more data, or maybe we need to include geophysics as a further constraint on our model. Whereas in the bluer areas, we might go, well, let's not waste our time collecting new data because it probably won't change the answer very much. So it's a way of feeding into value of information studies. Excuse me. So just moving on, of course, geophysics can be incredibly important, and some of the work that Jeremy Giraud has been doing, first in his PhD and now in a postdoc in Perth, but he's just recently moved to Nancy in France, has been looking at how to integrate geology with geophysics in a more routine fashion. And the way that he did it, the first method that he used, which is still very powerful, is to draw upon this idea that there isn't one single geological model which is correct. If we can automate the geological modeling process, we can try out many, many different types of models, and we can use the uncertainty in those models as a constraint on how much the geophysical model is allowed to vary. So on the left-hand side here, we have cross-sections through a 3D model. We have 6 cross-sections, and each one of them is telling us about the probability that any given voxel will be one particular rock type. So there's 6 different rock types in the model, and if it's black, it means it's low probability, and if it's white, it means it's high probability for each of those different levels in the stratigraphy. He then combined that with the uncertainty about the petrophysics. So we have petrophysical measurements, but they're uncertain. So this is an image of susceptibility versus density, and we can see that there's a probability density function for each of those. And he combined those with the gravity and magnetic observations in such a way that he could use the petrophysical the probability density function, the geology probability density function as constraints on the geophysical inversion, and then, which is what gets us to the reddish sort of model on the right-hand side, which is giving us predictions about lithology. And then he can go further, and he can use this idea that the topology, the spatial relationships, can actually be used as a constraint. So all of this work has been published now, so I'm not going to go into it in huge detail. It's also something that's very much, if you want to know more about this, talk to Jeremy. But his work has been really pioneering. It's not the first person to combine these types of data, but it's the first person to combine the petrophysics, the geophysics, and the geological uncertainty into a coherent inversion scheme. So the map to loop work has provided us with significant advantages because it's allowing us to reduce the time to first prototype models. We're not saying they're the best models we can produce, but they produce models. The time taken to produce that 3D model of the 1 degree area was about somewhere between half an hour and an hour, and it was fully automatic once we'd set up the system in the first place, and we could do choose a rectangle and draw a different model just as easily. The most important thing of all, though, rather than being fast, is that it separates out the primary observations, because we know exactly what the input data was that was used, the interpretations, the derived data, so those the work we did to combine different data sets, and any conceptual priors that we used during the data reduction step. So if we said, well, we don't know what the faults are, let's say they're all vertical, that's an algorithmic decision rather than it being a decision made by the modeler, which is lost once you've got your final model. The other side of it is that it provides a homogeneous pathway to sensitivity analysis, uncertainty quantification, multi-scale modeling, and value of information studies. So the work that we're doing to automate this process is not to remove the geologist from the system, but to put the geologist where it matters. So to put the geologist very early in the modeling process where we're deciding which faults we want to understand because we want to understand a particular mineral system, what is the nature of the mineral system, which faults are likely to be important in that mineral system, therefore these are the ones that we want to model. Then once we've made those choices, they're codified in a very transparent fashion so that you can go back and make a repeatable model. We can go back, the next person, if they make the same decisions, will result in the same model. But it's also so that we can then automate the process so that we can build 100 models or 1,000 models with varying either the starting priors, so maybe I want to try the faults all vertical or all dipping to the east, see which one of them gives me a better solution, but then use that as part of a larger pathway to uncertainty quantification and value of information studies so that we know where to collect new data. The logic is that we're going from this complex combination of inputs into 3D modeling to something where, in an ideal world, they're unbundled, and so you know exactly what you've done. And in the end, that's, in a way, trying to make 3D modeling more scientific, because you're trying to make every decision explicit in the code rather than being a rather random walk by the geological modeler. So just looking at the time, I'm just going to spend 5 minutes on a completely alternate view of how we can do 3D modeling, and then I'll stop for some questions. So let's suppose that we've got no outcrop. What do we do then? We have to throw away everything we've just talked about. No outcrop, very little drill hole data, which is the case over much of Australia. What are we going to do? We're going to try and go to something like machine learning, perhaps, or geophysical inversion. Both of them are perfectly valid approaches. I've already talked about geophysical inversion. Machine learning, I don't need to introduce to you. You all know what I'm talking about. But even in domains where machine learning is widely used and where they're huge data sets, like in the medical world, the reality is that labeled data sets that allow us to test machine learning are quite sparse. And in geology, they're almost non-existent, and in 3D geology, they are non-existent. There are no standard 3D modeling suites of 3D models that allow us to test either geophysical inversion codes or machine learning algorithms. And to be honest, these days, the distinction between machine learning and geophysical inversion is disappearing fast. So I treat them as separate here, but they're essentially going to be one and the same in the future, I think. So what we've been working on is building a suite of 3D geological models and their gravity and magnetic response that allow us to test inversion schemes and allow us to train machine learning schemes. So we've used Noddy. It's a package I developed a long time ago. Again, it's open source now. It builds a 3D model on an idealized description of kinematics. You provide the density and susceptibility of each rock type, and then you, because of you built a 3D model, you can actually calculate the gravity magnetic response. So it's a kinematic package, so you impose kinematic equations on the starting geology to result in a complex 3D geology, as we see in this cartoon here. And because we have control over the input parameters, we can randomize them, and we can make a series of arbitrary 3D geological models by combining faulting, folding, unconformities, plutons, all of these sorts of things. And here we see 100 different models at the bottom in terms of their gravity response, their geological maps of the top surface, and their magnetics. And working with a group in China, in Northeastern University, led by Zhangtong Gu, we made a simplified set of models, the 3 million different models of folded and faulted geology, which we could then use as a training data set for machine learning algorithms. And they fed this into a convolutional neural network. I'm not going to go into any of the details because of the time. And we were then able to, first of all, on the left-hand side, use it to recover the 3D geology based on the geophysics within the world of the 3D models that we produced. So we could provide it with any magnetic image from within that data set, and it could tell us what the parameters were for the model. We could also apply that to real-world data on the right-hand side, where we have a geophysical image on the top right of a syncline, and it could go through its trained data and pull back an interpretation of the 3D geology based on the geophysics image that it was seeing there. So this is a method that's still in its infancy. As part of this one was a very tuned solution. We only had 2 types of deformation. We've also put out to the public, and this is something that's just submitted, but the data is all there, 1 million models of arbitrary complex geology that, again, you can use to train yourself in interpretation of geophysics or train a machine. 1 million is not enough for the complexity we have here. It probably needs to be 100 million or maybe even 1 billion models, but each model only takes 15 seconds to calculate. So with a bit of patience, we can make much larger data sets, and we can tune these to specific geological terrains with the idea that if we have an area with no known geology at the surface, we can still build up a 3D model by using a machine learning approach. So that's that very quick addition. We're building 3D models as both training sets for machine learning, but as also testing sets for geophysical inversion. And that's all I'm going to say. 2 different approaches to the same problem. For the 3D modeling, it's all proof of concept, it's all open source, so you can download it, look at it, and try it out yourselves. The 3D models, there's 1 million models for you to go and have a look at. And I just thank the sponsors and thank you for tuning in and listening to me today. And I'll open it up for questions.
Thanks, Mark. If any of you have questions, please raise your hands or you can type in chat box. Mark, one of the quick questions which comes to my mind is that primarily you are using constraints which are geophysical in nature or in the geological nature. But if we want to even look at flows and other things, do you plan to involve geochemistry at some point of time, or kind of because when we are talking about permeability and other stuff, the geochemistry starts coming into there.
Yeah, no, absolutely. It's definitely something that's in the future of all of this work in two ways. One way, when we're doing the prospectivity analysis, if we have a prediction from the prospectivity analysis that a fault will be important, obviously understanding the alteration halos around those faults to see whether there's any evidence for that activity is going to be important. But it's also important in terms of mapping the geochemical variations that we can see in the context of the 3D models. So not just having surface maps of chemistry, but if we have drill hole chemistry, mapping that in 3D and using these ideas of geological distance rather than straight line distance as a way of better understanding and better interpolating geochemical signatures. So at the moment, geochemistry is either just simply Krieged or it's Krieged based on anisotropies assumed from fold patterns. But if we include non-Euclidean distances, so faster fluid along faults, we might end up with better interpolation schemes for the geochemistry that may result in better targeting as well. So absolutely, geochemistry is really important. We need the structural framework in which to interpret that geochemistry, but hopefully in the future that's coming.
And in case if we have paleo drainage systems and all that, those kind of stuff, can that be incorporated as a constraint in given, or is it work in progress?
Sorry, I missed the first part of that.
I said if you have information about paleo drainages, if somebody has mapped paleo drainages in that area and those kind of information which are not surfacial but has been marked. So, I mean, can we incorporate in the present system as a constraint, or is it work in progress?
It's definitely a work. I mean, there are many types of constraints. One of the sort of second order structural constraints are something that haven't been happened. So the idea that we might have bedding, but then there's a first foliation, then a second foliation, all those sorts of things. The structural modeling code will accept those as constraints. What we find is that in most cases it's not mapped at a regional scale, that you will find an academic has mapped some of these things for their own field area, but as soon as you're outside their area, there's no data. So like all things, the modeling is only as good as the data that you have available. So we have to, at any given scale, you're always going to be challenged by the fact that you have very heterogeneous data available. And so you can do more if you have more data. But certainly the idea is to go beyond just the surface mapping constraints, to use the drill hole constraints, to use geophysical sections, interpreted sections, as valuable inputs into the modeling.
There is a question from Mr. Pandey. How geophysical data can be used in model in form of raw data type or 2D, 3D form of geophysical data output? So basically, I think he's looking at, do we use raw data or we use interpreted data?
It depends. With seismic, reflection seismic, we typically use interpreted data because there are no automated systems. With gravity and mag, we could do inversions. With basically every geophysics has a different story. With gravity and mag, we can actually do the sort of integrated inversion that I talked about before, that Jeremy Giraud has been working on. With magnetotellurics, it's very difficult to use magnetotellurics without doing some form of interpretation of the results, because they tend to be quite smooth. Although we have students working on combining seismic interpretation and gravity in a framework that allows the 3D model to be built automatically. So there isn't one answer to that question. Every type of geophysics lends itself more to direct inversion or to having to have an interpretation step first. Certainly in hard rock terrains, which is where we focus, the seismic is very difficult to interpret, and there are certainly no automatic schemes for that. So we we necessarily pass by an interpretation stage first. For gravity and magnetics, because they're simpler systems, we can do some sort of joint inversion.
There's another question from Kavaria sir. That's basically, thanks Mark, great learning today on ML usage. Any example of testing of the outcomes? Any of these outcomes which you have done, have you tested on the ground? Or
well, I mean, one of the wonderful things about 3D, especially at the regional scale, is it's very hard to test, because all you can do, what we did with the I can go back and show that. What we did with the 3D modeling and the inversion of the data in this case, on the right-hand side, we have the 3D model as predicted by the machine learning. On the left-hand side, we have the 3D model as predicted by the automatic 3D modeling from surface geology. So we can see they're not quite the same. I actually think the one on the right is better in this case. But one of the challenges of 3D is that we don't have natural data sets which we can constrain our results against, which is why we went to this approach. You know, there are no libraries of known 3D geology. Each one of them is based on huge amounts of interpretation and unknown amounts of conceptual bias. So that's exactly why we went to this machine learning approach. But the only way we can test is systematically is against synthetic systems. There are no libraries of known 3D geology, because especially when you go to the regional scale, you're talking about something that's 100 kilometers by 100 kilometers by 10 kilometers deep. There's no way of testing it. But it's a good question. It's the limitation of all of the things we do in 3D, is that we'll never know the answer at the regional scale.
Absolutely.
I have a question, Mark. First of all, thank you, Mark. It was really a great presentation. I mean, it's giving a new dimension to the geological modeling. Now, I understand everyone has a certain method of approach when they start preparing geological models. But what is your approach when you start preparing a geological model? What are the basic things you you do or prepare, or is there any workflow which you tend to follow while preparing data sets, or you allow every data sets to come in and then you decide what should be taken or what not to be taken? So is there any, what do you do when you start a geological model right from the beginning?
Well, the first thing, we often have students that come to us and say, I'd like to build a geological model for my master's project. And the first thing we ask them is why? Why do you want to, A, it's painful, but why do you want to do this? What is it you want to learn from your 3D model? And that's something that there isn't a workflow, there isn't a specific workflow, but that question is the most important question that you can ask when you're about to build a 3D model, because it will determine which data you want to use. So, you know, if you only care about the top 100 meters, there's no point in most cases in using gravity. So you can throw out data sets that way. It also helps to determine which features in the geology are important. If all you care about is fluid flow, it may be that, you know, that certain faults are going to be important for your understanding and certain faults aren't, depending on whether they're before or after the formation of the ore deposit. So it's, you know, depending on the question, the first and most important step you can take is to decide what it is you really want to model, and therefore which data sets and which geological or geophysical features that you want to maintain in your model. There's no point in putting a feature in the model if if it's not going to help answer your question.
Right. We have Shantikumar sir to. Shantikumar sir, you can speak out your question, please.
Yeah. Thank you, Karunakar, and thank you, Mark. It was wonderful to hear you, and the entire initiative and the research which you have done it. It is more like how expert geological mineral exploration geologist thinks actually. Yeah, and it's even the data, because you're trying to combine the observations and the modeling and the uncertainties you brought into it, which is really creditable. But some of the things which I would like to, whatever I saw, it was very good. But there is something which I did not see, that is input of the drill hole data, because anything subsurface comes essentially from the drill hole data. Like,
yeah, no, it's a very good question.
Lithological, just let me come.
Yeah.
The lithological input at different levels of the drill hole, and also mineral content, as well as mineralization concepts. That, along with the 3D geological models. That means, in a drill hole, what you get is, you get the 3D geology as well as 3D, that means a depth-wise mineral distribution, what we observed along the core. So that probably, I'm sure that it must be taking it, if your package must be taking it. Then we play with your different algorithms and come out with the different models, and it gives more opportunity for the experts to narrow down to minimum models, which they can use them both for concretizing their models, as well as it helps further exploration, like extensions of the survey, extensions of the drilling. So I'm sure it's a very, very useful tool, what I see that. Good, it's very happy. But all that is important is, I think we need to take this system, work with our data, and see for ourselves how it is going to be is useful. But more important thing is, a lot of training is required for the people who are here trying to use this.
Okay.
As of now,
yeah, I'll take on your question about the drill holes. You're absolutely right that drill holes are really important and we can use them. However, at the regional scale, imagine that we're building a model that's 100 kilometers by 100 kilometers by 10 kilometers deep. Typically there, the size of the voxel that you're going to create, the cube that you're going to create, is maybe 100 meters. And we have huge amounts of drill hole data in Western Australia. 99% of that drill hole data doesn't go through the bottom of the first voxel. So all of that information is crammed up into a very near surface level. So if we're trying to build a model, we go back and look at one of these models that we've actually built, like this one. These voxels would be 200 meters by 200 meters. So everything that the drill hole tells us is what I said in the talk, is essentially it's like another form of outcrop in terms of how it constrains the deeper part of the model. Now, of course, you may not care about the deeper part of the model, but if you're trying to understand the regional questions, then the deeper part is often important because it's telling you about the deeper part of the mineral system. If you're concerned entirely with a 300 meter by 300 meter by 300 meter ore deposit, then of course the drill holes are perfectly adapted to constraining the 3D geology. But when you've got 100 kilometers across your model, then the drill holes are basically just tiny pinpricks near the surface. And they are useful, but they're not nearly as powerful as they are at the mine scale.
Okay, that's good. So I'm looking from my point of view that, most of the mineral deposits which in India, which we have about 1 to 2 kilometers prospect areas. So that's what I'm looking at.
Sure,
so
but if
the people would narrow down to certain area of maybe about 5 kilometers by 5 kilometers area, and then again further narrow down to about 2 kilometers by 1 kilometer strength.
Sure,
and
absolutely.
There they start with definitely detailed geological mapping on the surface, whatever they get, and then followed by a preliminary geological model, conceptual model. They go about, I mean, this is how any exploration geologist thinks. So they go with a model, then they go about by drilling and then get the data, and then slowly they build a model which helps them to give a correct subsurface phenomena and the shape of the ore body, and which helps us to resource evaluation as well as extensional drilling initiative.
Mark, can I come in?
Yeah, absolutely.
Yeah. Shantikumar sir, I understand what we are talking, but this is primarily to look at the regional scale. Let's say this is something which GSI or when we have a regional scale airborne studies, we have the mosaic geological maps, and we want to look at entire big area to find the projects for exploration. You know, this is the step one to find area of interest, then subsequently do the detailed exploration. So that's where this whole technology or this whole talk is focused, not as mineralization and subsequent mining and other stuff.
I agree. There's one more aspect I can say that, I mean, if such is the case, I think we in AMD and also GSI have got large airborne geophysical data collected, and also a reasonably very good geological maps. So they can be used here to help do a 3D modeling. That's usefulness.
I have Ash Johnson. Ash, you have something to say. Please feel free, Ash. Ash.
Yeah, thanks again, Mark. A great talk there. Very clear, very good at setting out those different concepts of how we look at the data, and I particularly like the uncertainty qualification and thinking about bias in modelling. And it actually, my question sort of touches on what Shanti sir just talked about there. At the mine scale, at the more regional scale, we have this discussion around the explicit and implicit types of modelling, sort of drawing lines, and I wanted to ask you about that in this regional context. I mean, what sort of role do you see for the explicit type of modelling in this? I mean, is this something that that people should consider if you've got 2D seismic cross sections, albeit distance apart, or is it really the implicit side of things that really brings its strengths to this type of modelling?
Thanks, Ash. That's a really good question. The horrible echo, so the answer to the question is, if you want to do uncertainty analysis of this type, you have to use implicit modeling, because it relies on the ability to produce variations on the theme of what's possible given the input data. And if you want to do that manually and to produce 100 models manually with variations in the input data, you will go crazy, because it will take you months and years of your life. And so by the time you do the uncertainty analysis, the mine is opened and closed. So it's really, at this regional scale in particular, it's absolutely essential to use the implicit modeling, because there's the companies that do modeling at the regional scale are doing it because they want to understand the mineral system, they want to understand the context of what's known in order to look for new materials. They have a turnover time of 2 or 3 years with the region before they either find something or move on. If you've taken a year to build a 3D model and then another 2 years to do the uncertainty analysis, you've totally missed the life cycle of that analysis. So for us, there's just no question, it's got to be an implicit scheme. It brings its own problems, don't get me wrong, implicit schemes aren't perfect either, but if you want to do the uncertainty analysis, which implies making stochastic simulations of variations in the 3D, the only way to do it is automatically and using implicit schemes.
Yeah, thanks very much.
I think, Mark, not many more questions. I would like Ash to give a conclusion, and then Drew can give a vote of thanks. Thanks for your time, Mark. Personally, I feel obliged to bring up all this with your assistance. Thanks a lot. Ash, you can have a closing comments as a yes.
Yeah. Well, thanks, KK, and Mark. Thanks again for a fantastic talk. I mean, I think as a recognized expert in modelling, I think this audience is actually very privileged to hear straight from the horse's mouth about the research that you and your fellow researchers are doing. I think we've all learned a lot from here about that ability or the necessity to really be able to separate the various parts of a model and determine the input to the data and determine how each data type actually contributes to the model. I think a major advance there that you're talking about really is that uncertainty modeling piece, because it really talks to that, particularly on the geophysical side. It really talks to that uncertainty and that ability to generate any number of models that actually fit the data perfectly well, but don't necessarily have any bearing on geological reality. Being able to bring in, create a 3D model from that surface regional data and being able to test it with the geophysical concepts and create a unified model is extremely it's an extremely rich system, and something that we need to be thinking about as a concept. The fact that all of this is being done in open source software is excellent. Clearly, there are a number of commercial packages that can take advantage of open source codes, but clearly there's also plenty of organizations and researchers, particularly at universities, that don't have access to commercial packages, and this will actually be something that they can get access to a very comprehensive advanced system to enable them to both develop those skills in geological modelling, and particularly regional geological modelling, and in the Indian context, of course, that's extremely important with the continental scale geophysics that's going on at the moment, and the desire for uncovering and realising India's mineral wealth. These concepts are really important for India. So once again, thank you very much, and yeah, it's been most educational. I'll pass that back. Okay.
Yeah, thank you. Yeah, thank you, Ash. Thank you, Mark, for today's presentation, and I also thank all the participants who have joined today. And please do join again for our next session, which is on importance of data quality, which will be on 23rd October. And thank you for joining today. And it will be delivered by Asmita Mahanta, who's geophysicist, head geophysicist in PHP. So we will hope we will meet you again there. And thank you again, Mark. Thank you, Ash. Thank you all the participants who have joined today. Thank you. Thank you.
Thanks to everybody for your questions. And just a plug for Asmita, she's going to give a great talk. She's here in Perth as well, and I couldn't recommend more that you listen to what she's going to say. So thanks everybody again. Thanks for your questions. I've really enjoyed this and look forward to catching up again.
Thank you. Thanks, Mark. Thanks, Mark.
Okay.
Thanks.
See you next time.
Bye. Bye.